Section 2.3 is going to talk about other properties of functions. So some of the properties we've already talked about are continuities and discontinuities. We've talked about vertical asymptotes, horizontal asymptotes. We've talked about holes. And then we've talked about basic shapes of end behavior of functions and things like that, okay? Now we're going to add in some of the other types of properties of functions. The first one is increasing and decreasing functions, okay? And I feel like this is pretty self-explanatory. A function is increasing when it is going essentially up from left to right. So increasing, it's moving in an upwards direction, or y is getting larger as we move from left to right. I just made that worse. So we're going up as we move from left to right. A decreasing function is moving down as we move from left to right. And a constant function is staying the same. It's got a constant value, okay? But the big one we want to talk about is increasing versus decreasing. So if you look at this graph right here, this section of the graph from A to B is increasing. So if we were going to analyze this graph, I would write the word increasing. And I would say that this function is increasing from A to B. And we're going to use the open set notation, okay? Because we don't want to use brackets, because at A and at B, the function isn't really increasing or decreasing. Those are points where it might change. They're called points of inflection. So they're points where it might change from increasing to decreasing, okay? Decreasing, I would write that word. And I would say this function is decreasing because it's going down from B to C. And then it begins increasing again from C to D. So I would write union C to D. And there's no other sections of the graph that are decreasing. There's also no sections of the graph that are constant. So this would be an analysis of increasing versus decreasing in this function. Okay, so we're always going to use the open notation, so always use the parentheses when you're talking about sections of the function being increasing or decreasing. And then we'll use union to say that we're going to put multiple sections of the function together. Okay, so let's look at the first example. And some of these examples get a little bit strange, but we'll go with them anyway. So in this first example, Grandpa George is 80 years old and is reminiscing about how his weight has fluctuated over his years. So he envisions the following piecewise graph in his head. Obviously, Grandpa George is very math savvy, so he's envisioning this piecewise graph in his head. And although Grandpa is prodigious at envisioning such graphs, his knowledge of increasing, decreasing, and constant has escaped him in his old age, which how he's envisioning this graph and doesn't remember increasing and decreasing, I'm not sure, but it's Grandpa, so we'll just let Grandpa kind of do his own thing. So they want to help him out by defining the open intervals on which his weight increased, decreased, and remained constant. So section A will be the increase section. Section B will be the decrease section. And section C will be the section that remained constant. Okay, so when we're talking about these intervals, we're talking about X value intervals and talking about what Y is doing. So looking at the first one, when he was born at 0, his weight started to increase. And his weight increased until we got to here, which is about 25. So his weight increased from 0 to 25, okay? After that, from 25 until about 35, give or take, his weight remained constant. So from 25 to 35, his weight remained constant, okay? And then from 35 to 40, Grandpa decided to put on a little more weight. So from 35 to 40, and 35 to 40, he put on a little more weight. And then at age 40, apparently he had a midlife crisis and decided, oh, I'm too heavy, I need to lose some weight. So he lost some weight, he decreased until he hit 50. So from 40 to 50, his weight decreased. And then from 50 to 80, Grandpa was doing a really good job at maintaining that weight. So from 50 to 80, he has a constant weight again. So this would be an analysis of where his weight was increasing and decreasing. I feel like it's pretty easy to see on a graph. It's just making sure that your notation is correct, okay? So make sure you're not putting the decreasing or the increasing in the wrong section. And make sure the other error that people make, make sure that these intervals are all in terms of x. In terms of x. So we're talking about the y decreasing and increasing and being constant in terms of x. So from 0 to 25 on the x-axis. So make sure you don't mix that up. That tends to be a common mistake. All right. Then in the next section, they're not going to actually give you a graph. They want you to, without a calculator, list the open intervals on which the function is either increasing, decreasing, or constant. They want you to do it without a calculator. A sketch might help. So we should be able to sketch these just from our basic knowledge of functions. Okay, so let's take a look at A. This is a cubic function, and it's a cubic function with a positive coefficient. So cubic functions with positive coefficients look like this. Okay, that's a basic graph of what that function looks like. Well, if that's what the function looks like, this function, as we move from left to right, is increasing the entire time. Okay, there's no part where the function is constant. There's no part where the function is decreasing. So this function is increasing for the entire domain. Okay, and I don't feel any need to write that it's not decreasing or not constant, because we already said that it's decreasing or increasing, excuse me, for the entire domain. So we don't need to write anything else about the other section. Okay, look at this one. This is a squared function. So this is a parabola, and this parabola shifted over 4 units to the right and flipped upside down, okay, and stretched. So if we have a parabola, it normally starts at 0, but now it's going to start at 4. It flipped over, so instead of going up, it's going down, and it stretched. So it's going to look something like this. Okay, so look at this function. So this function is increasing until it hits its peak right here, and then it's decreasing after that. Well, its peak is going to be at 4. So this function is increasing, and I'm going to put it underneath it because I just don't have space, from negative infinity to 4. That's hard to see. Increasing, whoop, there we go, from negative infinity to 4, and then it's decreasing from 4 to infinity. Okay? And I can tell you that on this one, there's people who will miss this because it looks like this function is going to negative infinity. So don't get mixed up between the end behavior and talking about the interval at which it's decreasing. So it's increasing from the x value of negative infinity to 4, and it's decreasing from the x value of 4 to infinity. Okay? So don't get confused about that. And then h of x is a rational function, and it's a rational function that has an issue at -3. And that issue is going to be an asymptote because there's not that same factor on the top, so it's not a whole. So at -3, I know that there's an asymptote. Okay. And because the exponent in the denominator is larger than the exponent in the top, I know that there's also a horizontal asymptote at 0. Okay. So now I just have to figure out which ones of these boxes it goes in. So if I plugged in, let's say I plugged in -2. So if I plug in -2, this gives me a positive on the bottom and a positive on the top. So it's in the positive section. Okay. And if I plugged in -4, I get a negative on the bottom. So that's going to be in the negative section. So that's over here. So this function looks like this. So this function is decreasing. And then when I pick it up over here, it's decreasing again. So this function is never increasing, but it also doesn't exist at -3. So we can't say that it's decreasing for the entire domain because at -3, it doesn't exist. So we're going to say that it decreases, or decreasing, I guess, is what they said to use. So decreasing from negative infinity to -3, where it doesn't exist, and then from -3 to infinity. So from negative infinity to -3, and from -3 to infinity.